Hello again, and welcome back to my computer vision channel. Today we are going to read the source code for Codetr. So a couple of words about this model. First of all, this is the object detection benchmark for Coco dataset, which basically contains the history and leaderboard of different object detection models. Here we can see such stuff as Decoder, Deformable Decoder, faster CNN, YOLO, and then over there, all the way in the top, is Codetr, which is current state of the art, the best model out there for object detection. So this is what we're covering right now. This is the GitHub repository for Codetr. I'm going to say that it took me a while just to install it, and the primary reason for that is that it's built on top of MMCV and MMDet libraries. So MMCV in itself is basically a collection of primitives for computer vision built on top of PyTorch, and in general it is quite clear, and the same can be said for Codetr as well. So compared to other data-like models that I've seen, the code is rather clean, but there's one but. They actually just copy-pasted the entire MMDet library as part of the repo itself, which is a bit unfortunate because that sort of locks you into this old version that is copy-pasted, which in turn locks you to the old version of MMCV, PyTorch, CUDA, and all of that, which basically means that it's not really that easy to install. You cannot just create a Conda environment and just install all the versions. You actually have to install older NVIDIA drivers with older CUDA. All of this I talk about in my guide that I publish in my repo. I'm going to leave the links to that in the description. And so what I do here basically is explain all the steps to take to install all the dependencies and actually run the model, as well as set up the debugging thingy. I only managed to make that work on an NVIDIA GPU with CUDA 11 drivers. Although it should be possible to run that on CPU as well. In fact, this is the first model that I've seen that actually implemented deformable attention layer on CPU. So we're actually going to take a look at that in this video as well. And this is the paper itself for Codetr. In the paper, they basically talk about how they take just a vanilla Decoder model or Dino and then place more old school convolution-based models like ATSS and faster RCNN on top of that to speed up the training, to help the training, and then that setup is basically thrown away during inference. So for me, for someone who've read a lot of code regarding transformer-based models and Decoder, I'm quite confident about the Decoder part, but then ATSS, faster RCNN were quite new to me. So today we're going to take a look into them as well to make sure that you haven't missed a thing in computer vision of the past decade. So we're going to read into them as well. And this is the plan for today. So we'll start with basically my Jupyter notebook that does the same thing as the training script, but in a more sort of linear laid out fashion, where we can actually take a look at the images that the model is training on, execute them interactively, see what sort of augmentations used, and so on. Then we'll take a look at the actual code of the model, which is completely different to what I've seen before in other Decoders, because it's based on MMCV, but it's more or less the same logically. In particular, we are going to take a look at this deformable attention layer, because there's one implementation on CPU which will be much easier to read. So I think that will be helpful to a lot of people. Then we'll read the CNN part of the models, the auxiliary parts like regional proposal network, the regional refinement part like RCNN, and the ATSS. So we're going to find out what that is. And finally, we're going to, so in this part with the CNN part of the model, we're also going to take a look at how they connect to encoder and basically helps train the encoder. And then in the final part, we're going to see how these auxiliary heads also help with query generation, with queries then fed into the decoder to help train the decoder. And so let's start with my Jupyter notebook and datasets and Dataloaders. So this is my setup, my Jupyter notebook, which I've put in the root of the Codetr repository after installing all the dependencies. So by placing it at the root, I can basically just copy paste code from different scripts like train.py, for example. So here we have a lot of imports. Some of them are just like normal outside libraries, and then some of them, like this one, are actually just written right here in Codetr repo. And I can just sort of copy paste the same code and import it, and it will work in my Jupyter notebook the same way as it does during training. So I'm just going to execute this. So I have a couple of scripts to basically just plot the results. Here I have set up for arguments. So this is why it's useful to just print out them at the very beginning of the training, because then you can just define this argparse.namespace class and pass it around in your code as command line arguments, because otherwise it will be quite hard to set up command line arguments in Jupyter Notebook. So instead I just do it like this. I also set up some environment variables that are needed for the sort of multi-process training used in this particular model. I'm not sure what it is, but basically my world size is 1, which means that I'm not doing any parallelizing, but I still want to run that code. And the rest of the stuff I just basically copy-pasted from train.py. So a lot of this is just mundane stuff. So setting up autoscaler configs, and then someone here I have the actual model. We'll take a look at that later. Datasets. So the datasets object, upon creating this, I think it's part of MMCV, prints out the statistics about the dataset, like what each of the labels mean and how many of those we have in the dataset. So you can see here that 0 is a person, we have a lot of them, and then a lot of cars, bikes, not so many hairbrushes, for example. So this is some interesting statistics, and this is how we can get the actual image out of that. And so I just pass that to my plot result function, and this is how it looks like. So this is all Coco dataset. So Elvis dataset also actually uses the same set of images. So here we have person on the bike, and so we have bounding boxes, class labels, and the actual picture. If I just press this execution of the cell a few times, I also get a sense of what sort of augmentations are used. So you can see here that the image flips left to right from time to time, and then it shifts around a little bit, like now, for example. And this is basically the random resize crop. But other than that, we don't really see that much image augmentation going on. Codetr doesn't use that much of that. So we can take a look at the actual image and see what's in there. So we have some meta information about the image. We have the image itself. We have ground truth bounding boxes, which are just basically 4 numbers for the coordinates. And we have ground truth labels. And we can use that as a dictionary. So if I just index into the img, and I can get the shape of the data. So it's 800 by 956 image, 3 colors. And let me grab the second image, for example. So this is a different image, and we'll see that the size of the image is different now. So all of them will have slightly different sizes in our dataset. So then we have some more really important code that I will not going to explain because it's just copy-pasted from the string.py script. And so here we have the data loader. So the data loader is responsible for taking different images from the data set, randomly usually, and unite them into batches. And you can see the artifact of that. So first of all, now samples.img should have 2 images at least. So I think we have a batch size of 2. And the shape is now 2 by 3 by 923 by 800. So now we have 2 images in a batch because batch size is 2, and 2 images which most likely had different sizes were padded to the same dimensions. And you can see the artifact of that if you plot it. So this gray area at the bottom, in this case, is the padding that arises when you try to basically unite two images of different size or more images of different size into a single batch. But this part will basically be ignored by transformers thanks to the attention masks that we also pass to the model. And this is how we can plot the model. So it all looks quite easy, but I spent like 3 weeks trying to install it all, trying to launch this code correctly, actually initializing the model in my own Jupyter notebook. But that makes the remaining part much easier. So this is it regarding Dataloaders. The rest of the video, we're basically going to debug into this one little line of code, actually reading all that is going on within there. As you can see, it also computes loss. So pretty much everything is in there. So now let's dig into the actual model, starting with the transformer part. So first, let's find out what the model is. I'm just going to print out what it is. And so here we see that it is some sort of distributed data parallel wrapper, and the model itself is called Codetr. So to break somewhere, I need to find where it's defined, and I'm just going to type in the search class Codetr. You can see there's just one like that. So here it is. And then when we call it, we use this call method, right? And it's actually no call method here, no forward method as well. But it's inherited from this base detector. So base detector is present here, and we can see that it basically, if return loss is true, which it is because it is by default, it is just calling this forward train method. The forward train is the one we should be looking at. So let me put the breakpoint here and see if it works. So now I'm calling debug cell on this one, and hopefully I will arrive where I need to. And here I am. Right. So we are here in Codetr forward train. So I'm just going to quickly validate that nothing unexpected has happened to my image. So I still have batch size of 2 images, 3 colors, 923 by 800. So it's still the same images we've seen before. I will make sure of that by setting the correct seed. And so this is the forward call. So this is actually the sort of outer layer of everything that is going on in the model. So in here, we'll see this extract features call, which is basically calling the backbone. Then this query head, which is basically the transformer, the data part of the model. Then RPN, regional proposal network. Then region of interest pooling, which is like the second part of RCNN that actually refines the proposed regions. Then the one called in the code bounding box head, which is ATSS. And then finally, this part about positive query generation for decoder. So it's all basically high-level strokes about what is going on in the entire model. And so this is the diagram of the model itself. So we've seen the backbone, it's called extract features, then the query head, this is the query head, then we have all the auxiliary heads. So we've seen 3 of them. One was called RPN, another one was called ROI, and this final one was called bounding box head or ATSS. And then this connection to the bottom, this is basically just output of these auxiliary convolution-based networks being connected directly to the loss, which is the same as saying that let's let them just detect objects, and we use this training signal flowing backwards all the way to the encoder to improve the encoder. And then this part of the picture is this positive query generation, where we basically say that our CNNs have detected something. We're going to use these detections as extra signal that we pass into the decoder, letting the decoder basically fix the errors of the CNNs, and that's a useful training signal, thus propagating useful signal to the decoder as well. And so coming back to the code, let's read this feature extraction. I'm just going to go to definition here. Again, I'm not going to dig in too deep in the backbone code, but just sort of executing it and seeing what happens. So in the current config, the backbone should be ResNet. So it's a bunch of convolutions. Here, it doesn't really have a common name for, oh yeah, actually it does. So it's called a ResNet. It's basically a bunch of convolutions. And we can see that the length of output is 3. And the shapes are like this. And what is basically going on here is like every convolution in the ResNet at least, or almost every convolution, will be taking some sort of image, starting from the original image, which has quite high dimensions, but then only 3 colors, only 3 feature channels as we call them. And then they basically will be projected down in the resolution to a smaller image, but the number of channels, number of colors that being passed in will increase. And so we've seen that, we can see that the output will take these 3 stages of the process, where the first stage has 512 feature dimensions and then like 100 by 100 spatial resolution. Then the second one is 1024 feature dimensions and then like 50 by 50 pixel resolution. And the final one with 2K feature channels and 25 by 25 pixel resolution. And this is a good illustration of that from Deformable Decoder paper. So we've started with the original image, and then each newer version of the image is smaller, but then it has more feature channels. And the reason we can afford that, and we want to afford that, is that now we have deformable attention, which is basically linear in time complexity with respect to sequence length instead of quadratic. So we can afford to pass in more stuff in there. And the reason we want to afford it is because we are doing object detection that really does need this high pixel resolution in order to plot accurate bounding boxes, especially for small objects. And then we also have this neck. Let's just quickly print out what that is. It's a bunch of convolutions again, this time much simpler. So we have 4 of them projecting stuff down to 256 feature channels. And then this extra one is actually going to create another scale for us. So let's just print what we get. So we get out 4 sort of images of different scale, and the shapes are almost similar to what we had before, but now we have this 4th image that is even smaller, like 15 by 15. And the feature dimensions of all the levels were projected down to just 256. So this is basically the same as adding this extra layer on top of what we got out of the backbone, basically by applying our own convolution to the last layer that we had and getting another smaller layer. Let me return to this forward train method. So we've now applied the backbone. The only result of that is that now we have 4 images that are already processed. And the next, as we see here, will be the actual transformer. So this query head here is everything from here to here. So that's encoder and decoder at the same time. So next we have this losses object. So we are going to calculate losses along this forward train path as well. So we'll have to be aware of that. And this next line is applying this transformer. So let's just print what it is. So self.queryHead. Type of that is Codetr head. Let me just search for that. There it is, and we apply the method called forward train. So the forward train method itself is quite short. It basically applies the model self of x and then computes the losses. And also note here that we have these encoder outputs that are returned from this forward train call and not decoder outputs. This is because the output of the encoder is going to be fed as an input to the auxiliary heads, and the decoder output is basically used to compute the loss and nothing else. And to get this actual forward call, I'm just searching for forward. Here it is, and let me just break at the very beginning of it. So let me just validate that the object that we get as an input is still the same one, so it's the features we've seen with the length of 4. So one thing that we'll need to do before applying the transformer is deal with the masks. So remember that the picture that we're going to use looks like this. So because we basically pad all the pictures to the same size in the batch, we have this padding area that we have. But that's on the original image with like high pixel resolution. Now we get in the mask that says that this is the real input and this is just the padding. And now we need to project that mask down to the same feature scales that we have coming out of the backbone. So this is what happens here. So we basically interpolate the mask to have the same representation of 4 levels for the mask as well. And another thing that we do here is apply this self.positional encoding. So positional encoding is basically encoding the position of the pixel into embedding itself. So let's print what the type of that is. The type of that is sine cosine embedding. So we're not going to look too deep into that. Just maybe find the definition. The forward of that basically takes in these pixel coordinates, so to speak, and then basically compute different values for embedding coordinates as sine or cosine function of its position. All of that is happening here, so let me just continue. So the input to the transformer now is going to be this m-level fits, which is still length 4 m-level masks, which should be of the same length. Positional encodings, which I'm guessing are going to be the same length as well. So let's dig further. So we call this transformer. The type of that is Deformable data transformer. So let me break at the forward method of that. Continue. So next we need to flatten our input. And so we will basically iterate over 4 levels, flatten all of them, concatenate into one big object for masks, for position embeddings. Another interesting thing happening here is going to be the level embedding, which is now the encoding for which level the pixel was located in. And finally, these valid ratios and reference points. So we'll talk about all of that now. So first, what is the self.level embed? So this is basically just a parameter. So the shape of that is 4 by 256. So unlike this sine cosine position embedding, for levels we just have one trainable vector of parameters for every level. We are not doing any sine cosines in here. Let me just continue until after the flattening is done. And so we will have this for feature flatten object. The shape of that will be 2 by 15k by 256. So 256 is like a common embedding dimension that we'll see throughout the transformer. Batch size is 2, and the 4 scales that we had, like 100 by 100, 50 by 50, 25 by 25, 15 by 15, were all flattened out, concatenated into this one big sequence. So it is quite big by transformer standards, but since we are using deformable attention, it will be rather cheap for us to process that. Next, we have these valid ratios and reference points. So let me quickly explain how deformable attention works. So basically, normal attention, to compute that, we take some sort of input, which is an image, a feature map, and then basically compute all the pairwise interactions between the pixels, where each interaction, like we have embedding of one pixel, embedding of another pixel, we basically compute the dot product, which is just one number that corresponds to like the attention weight that we have to take this pixel with. So we basically do all the pairwise quadratic complexity computation for the mask. And then we get the mask, which is of the same shape as the image, but now each element is just one number, the weight. And then we basically multiply this image by the mask again to get the output, which basically now contains this next level representation where each pixel had the chance to communicate with each other pixel. So in deformable attention, the main difference is that instead of computing all of these pairwise interactions, we're just going to compute like 3 of them, right? This is much simpler from a computational perspective, and we want the locations of them to be trainable. So we basically just predict where we need to pay attention to instead of just computing attention between everything, right? But we also want to make that relative, because like if we are detecting, I don't know, football player head, for example, we want attention to depend on relative position of this object, right? So we can't just say that, take this particular pixel within the overall image, because obviously where to look depends on where the object is. So the points that we need to look at, their locations should depend on the location of what we are detecting. So that the predicted offsets should be relative. And so the way it's done is we have some sort of reference point that basically defines where we start to compute the offset. And then we have predicted offsets that are basically trainable, that tell us where to pay attention to. And so these reference points come in 2 flavors. So we have 2 sources of deformable attention in the model. So we have what is called self-attention when we compute attention between image and image, and the cross-attention when we compute attention between queries and image. Now, for image-to-image attention, the logical reference point is basically just the projection of the same pixel location within scales, right? So, for example, when we compute attention between this small scale and this small scale of the same shape, this is just obvious. It's just this pixel right here, right? So just the exact same pixel. When we compute attention between this small one and this big one, for example, we need to project it down somehow to find out like where in this bigger resolution image this exact pixel was located. So this is one complexity, and these are basically called reference points. Second complexity, as we've seen, is the valid ratio. So this process of projecting pixels down or up in different resolution pictures is further complicated by the fact that you have padding, right? And this padding will have slightly different pixel sizes, slightly different pixel proportions on each of the scales because of how it was done, basically using an interpolation. And so the valid ratios basically tell us, like in this particular pixel resolution input, what is the ratio of padding to non-padding, basically, so that we can restore original pixel positions. So this is what these reference points and valid ratios are about. Let me just continue until here. And so reference points, let's look at the shape, right? So it's 2 by 15k by 4 by 2. So each point is 2 coordinates, x and y. Then we have 4 deformable attention points. So each point in the input will attend to 4 other points. And let's see, valid ratios. Valid ratios is rather a small one, which just says, these are the padding to non-padding ratios for each of 2 images. And from this, we can tell, for example, that one image was like wide and then another one was tall. So we get padding from different sides here. You can also see that these ratios are slightly different for different scales, right? Because you might have like 12 pixels for 12 pixels worth of padding in 100 by 100 image. And then when you shrink that down to like 15 by 15 image, like 12 is not divisible by that. So it's either like 1 or 2. In this case, it seems to go for the lower one. So it goes to 1. And so like 1 divided by 15 is slightly less than 12 divided by 100. And so you get these different ratios. So next we have encoder. So let me just type out what that is. Data transformer encoder. Trying to find that. There it is. So it doesn't really have much code, so it just initializes something, which basically means that everything that is going to happen within this parent class transformer layer sequence. And if I go to that, so I'm going to definition, I will notice that now this is a library function. And to make sure that you can actually debug there, I'm just going to VS settings code, VS code settings, sorry, and just search for an option called just my code. And make sure that in both cases it is not checked. Now this option, which unfortunately is true by default, prevents debugger from going into library code. So we have to uncheck them if they are checked in your case. And then you will be able to debug into these functions as well. So I'm putting the breakpoint here, and then I continue. And here I am, right? So this is like the power of Python, that everything is basically Python code. You don't have to like compile it before executing. So here, although this is library code downloaded from the internet by pip, I can still read it. Here you can see that it's located in my miniconda environment, Python 3.10 site packages MMC. So this is the code of like the MMCV package that I download using PIP. So again, not much code here. So just a reminder, we've just entered the encoder, which just iterates over layers. So let's see what the first layer is called. They all are equal. So this is the base transformer layer. Let me just print out what that consists of. So it's a base transformer layer that consists of a list of modules like multi-scale deformable attention, feed-forward network, and some layer normalizations. First, let's find this base transformer layer thing. Okay, so here it is. So the forward method of this. Okay, let's just break again here and continue. So we are now inside this base transformer layer. So this is one of many layers of the encoder. And I have this operation order, which says self-attention, normalization, feed-forward network, and again, normalization. So this is basically MMCV's way of writing the code a bit cleaner. So we basically iterate and then apply the typical stuff that we usually have in our attention layers. So the actual attention, then normalization, residual connections, feed-forward network, and again, normalization. And then the actual attention here is called multi-scale deformable attention. And again, this is a library function, but we can still read it. Here's the forward method. Again, continuing here. We've come by, like we came down 3 classes, but the actual input is still the same. Let me just print it out. So it's still our slightly permuted tensor with 15K sequence elements, 256 embedding dimension. Value, where did value come from? Missed that somehow. Maybe let me try to find it. Yes, I came back a little bit to the encoder. So in encoder value is none. And then next breakpoint was base transformer layer. Again, value is none. Interesting. Then I apply it, and I just pass in this temp value as query, and TMP value is also equal to query. So yeah, at this point, value is basically equal to query. So what happens next? We save the identity for this residual connection. We add this query positional embedding, which by now is basically the sum of sign-to-sign embedding that we get from just pixel coordinates, plus the level embedding, which is just a trainable vector. So we have this value projection, and I think we'll have query projection somewhere here as well. And then we actually have these sampling offsets. So again, to get the actual points we're going to attend to, we have our reference points, which we already have. They're fixed. They don't depend on the actual content in the image. They just depend on the current pixel coordinate. And then we have these sampling offsets. So sampling offsets, the type of that is just a linear module. And it's basically a projection 256 to 256. Continue here and then here. And just print the shapes. So first of all, like we had these, it sounded like a simple projection, right? Just one embedding to another embedding. It's a bit more complex than that, as we see after this complex reshaping operation. So we now have like this 256 embedding is now split up into 8 by 4 by 4 by 2, right? So what is that? So this 2 here stands for X and Y coordinates. Then we have 4 feature scales. So we are going to attend like every scale to every scale. So every scale, every pixel in a certain scale is going to attend to 4 other different scales. And then every pixel will attend to 4 points in each of the 4 scales. And this 8 here is the number of heads. So let me just confirm that. So self.number of heads is 8. So again, coming back to the picture here, instead of basically computing one set of these fixed number of points and actual attention, we repeat the same process 8 times. So we have independent 8 attention matrices or 8 attention sets of points. We project the input value 8 different times into 8 different images and then basically concatenate the embedding coordinates of them. Same goes for attention weights. So self.attention weights is again just a linear projection, now slightly smaller. So the shape of that is 2 by 15K by 8 by 4 by 4. So again, 4 scales, 4 points per scale, 8 attention heads, but then attention weight is just one number. And again, coming to this picture, so in full pairwise self-attention, to compute the attention matrix, we do these dot products between each pair of points, right? So this is, and the output of the operation of dot product is one number that is called attention weight that tells us with what weight should we take this pixel in the output. So here, instead of doing this pairwise calculation to get the attention weight, we again just predict it, right? So this is the same as saying that instead of like this point, or as it's depicted here, like this point, attending to this point to get the weight of that, we just take the product in full self-attention, and in deformable attention, we just take a look at one point, just one, not two. Just project that down using a linear layer, which tells us, okay, so this attention weight should be 0.37. Right? So this is another major difference of deformable attention to normal attention. Then we actually apply these offsets to reference points to get these sampling locations. So, and here's the actual operation of using these sampling offsets to compute the output. So unfortunately, my code is compiled for CUDA, and CUDA kernels are not easy to read. But here is the CPU version. So thanks MMCV for the CPU version. We wouldn't be able to debug through it, but at least let's take a look at that. So basically, in what is happening here is we have the value that we need to index into. And we have these sampling locations that provide the index that we need. And then we use this PyTorch functional thing called grid sample. So we can just search, and it just tells us that it's a way to index into a basically tensor that has a bunch of coordinates, but then it's basically a two-dimensional, like a picture, and then each pixel within that dimension will also have the certain number of channels, and we also have a batch dimension. So the actual shape of the tensors would be 4D, but we know that it's basically 4D tensor that represents some sort of 2D image. And the explanation for that is, like, imagine that you have a tensor, let's say with the values 10, 20, and 30, right? So you can index into that using an integer index, right? So you can say x from index 0, and you get out the 10. You can get x with index 1, and you get out the 20, right? So the sampling operation is the same as saying that I want index 0.5, right? So naively it won't work, but this sample operation will basically try to fetch you the value corresponding to this non-integer index 0.5, which will be somewhere between this 10 and 20, right? So 0.5 is like in the middle, so the output should be 15, right? And if you want it like 0.3, for example, then it will look at this linear interpolation, and there will be something like 13, right? And that is for one-dimensional case, right? So I have just one dimension in this tensor. And so in each such case, to compute the output value of this fractional index, I'm looking at two neighbors of this location. And in deformable attention, we have a grid, an input 2D plane, basically. And to get the fractional indexing into that, we now need bilinear interpolation, which is the same as saying that I have like a 2D grid of points, and I'm going to use 4 neighbors to compute pretty much the same, the something average between these 4. Now, what that gives us is that now this sampling operation is differentiable with respect to index, right? So it wasn't before, so it's not possible to make it differentiable with integer indices. We don't know how to compute gradients with respect to something integer, but we do know how to compute gradient for floating point numbers. And so this is what we do. So now we basically can compute gradient with respect to the index, meaning that we can basically train this part of the network that is responsible for projecting the sampling offsets, which will push these sampling points somewhere where it's better for them to be. So it will basically train to look at desired locations. So now we've looked at the encoder, which basically takes in the sequence of tokens, projects that down to the same shape. So the output of that is called memory, is still technically representative of the original image shape that we had. Next, we'll see how to set up queries for the decoder. So this is this arrow right here. There's nothing new in Codetr regarding that. So all of the logic basically comes from Dino and Deformable data. And there's basically 2 major ways of setting up query. So the option number 1 is to just have statically initialized trainable embedding vectors, which means that the actual embeddings coming into the decoder will not depend on the image. They will always start from the same point, but they will be trainable. Second way is to generate proposals in the encoder itself, which basically means that we're going to treat this part of the network as some sort of detector. So we'll take output embedding from every token, we'll project that down to class probabilities, bounding box predictions. So we basically treat encoder as object detector. And we connect that to the loss as well to make sure that encoder does actually detect objects well. And so we'll take these predictions and basically select top 300. So remember, this whole sequence is something like 15K tokens. We'll select top 300 based on predicted probability. So the higher probability of some class that you're predicting, the higher the chance you get selected. And we will get the bounding box prediction out of that token and basically generate the input to the decoder. So what Codetr and Dino actually use is called mixed query selection. So decoder input can be seen as basically content part and positional part. And so in Codetr, content part will come from the statically initialized queries, and then the positional part will come from encoder proposals. So here it is in the code. So we've just called the encoder. The output of encoder is called memory. We can validate that the shape input and shape output is the same. So the features shape and then memory shape are exactly the same. And then we have these query generation process. So I've made a video about that before, about Dino. So here we basically take encoder output proposals. So this is a rather complicated function which deals with all the geometry, and the function of that is basically to be able to convert the relative predictions of bounding boxes that we get from every token into absolute coordinates. So we take the actual, so the output memory, we apply this regression branches, which stands for basically just a linear layer that takes in token embedding, 256 dimensions, and project that down to 4 bounding box numbers. And we add these output proposals because we want to predict relative stuff all the time, but we want to convert it to absolute coordinates. So the encoder classification output is obtained using this CLS branch, which is again just a linear layer, 256 in, 80 out. And then we generate the actual proposals using this torch top k method. So top k is 300 because we need 300 queries for decoder input. We select top 300 out of 15k tokens that we had using this torch.topk method. And then we basically get out the actual bounding box predictions and classification predictions corresponding to these 300. So one interesting detail here is this generation of proposal positional embedding. So basically what we will pass into the decoder will be this post-trans out object, which is generated out of this generated coordinates. No, sorry, it's not executed yet, so let's continue to here. We have these top k coordinates, which is basically 300 by 4. So 2 is the batch size. For every batch, we have 300 proposed tokens, and for each of them, we have bounding box predictions, so 4 numbers. And then we want to convert that to the actual embedding that we want to feed in to the model. So we basically take these 4 numbers and convert them to 112 numbers. And this is done using this get proposal pos embed function, which we will not dive in too deep into, but this is basically sine cosine positional embedding. So in general, positional embedding is something that converts a set of coordinates like x and y into an embedding of some shape like 256, for example. So we've seen that before in basically the backbone output, where we had x and y pixel coordinates that we expanded into an embedding using positional embedding. And here we do the same, but now instead of 2 coordinates, we have 4 coordinates, and we get 512 out. And I'm mentioning this because this is going to be exactly the same process as for this auxiliary query setup. So auxiliary heads, basically convolutional neural networks that also do some detections, will be used to generate some detections, basically. So these heads will generate bounding boxes for detected objects. We will take these bounding boxes, these 4 numbers, will expand them using the sine cosine position embedding into an actual embedding vector. And this is going to serve us as query input in this extra head here that helps train the decoder. So then we see that the actual setup is mixed selection. So we basically take in just the half of the 512 for the positional part, right? So this post trans out was the positional sine cosine encoding, and then the query part is this query embedding. So query embedding actually comes as function input, but this basically is just a trainable embedding vector. So this is basically saying that, you know, half of decoder input is static, trainable, and half is generated from bounding box proposals using this sine cosine embedding. And then we call the decoder with this. So decoder gets in query pos and query. So now let's read what is happening in the decoder. Once again, this is the same part as in Dino, so it's not really new stuff. So here's the actual call. So you can see that the key is not used because we're using deformable attention that basically doesn't need keys. We use query that we've just set up. We use memory as sort of side input. We also pass in the reference points. So reference points, as we've talked before, are basically the centers of attention in the deformable attention case. And so in the encoder, when we basically took a picture and passed it through the transformer layer to get another version of the picture, we used the output pixel coordinates as this center of attention, which will not be possible for decoder, because for decoder, we don't really talk about pixels, we talk about queries. And so for queries, we need some sort of mechanism to generate these reference points. And reference points we get just from the proposals that we had, which sort of makes sense. So we're saying that we now have 300 query inputs that basically corresponds to some initial versions of detections that we had. So we basically let our encoder try to detect something, generate actual bounding boxes, and then we use those bounding boxes as the actual query embedding source, but also we just take these bounding boxes and treat them as the actual reference points, so the new sets of attention for the decoder. And then we call the actual decoder. So let's take a look at the type of the decoder. So the type is this co-deformable data transformer decoder, which is defined in the same file over here. So let me just break at the forward method. So continue. Let's quickly take a look at the inputs. We have query. Query shape is now 300 by 2 by 256. And then we basically call the layers one by one. And after each layer call, we also do this reference points update. So we basically call layer by layer. Initially, we started with reference points corresponding to detections of the encoder. But obviously, after the first layer, we basically have a new version of that detection that is now better, closer to the truth. And so we're going to update the reference points to refocus our attention to these updated bounding boxes. And that's about it in this file. But the actual logic now is written in this layers. So let's see what the actual layer is. And the layer is data transformer decoder layer, which is also defined in the same class. Oh, actually it isn't. It's actually defined in a slightly different file, but here it is. You can always just find it using search, thankfully, because this is basically the mmdet that was supposed to be a third-party library, but it was just copied into the Codetr, so we can read it. We can see that it's a function that just inherits from base transformer layer. We've seen this one before. So here is the forward method. It basically iterates over the operation orders, let's just continue to here. So we've seen that in the encoder, the base class is the same. Now we can see that it's self-attention, then cross-attention, normalizations, feed-forward network. Let's see what we have for attentions and self-attention. So self.attention, multi-head attention. So this one looks like just the normal full pairwise attention. So we use that as self-attention, basically query to query. For cross-attention, let's continue to here and see. So for cross-attention, we have this multi-scale deformable attention thing, right? So let's try to find it. That's probably the most interesting part in the decoder. Let's just continue to here. So now this basically is one layer of the decoder. On part of the layer of the decoder, so we have query, value. Both have different shapes. So query is the actual query input that we had. But we also have this query pos input. So these are actually different, although they have the same shape. So this is what I was telling about when I told you about the content part and positional part. So the query part, which is the content part, it is basically going to be updated every layer. So the output of the previous layer is going to be the new input of the next layer. And then query pos is just static, so it's not really updated because it only depends on the position, basically. So we can see here that position embedding is firstly just added to the actual content part. And then we have the actual laid out code of deformable cross attention. So we've applied our positional encoding similar to what happened in the encoder. We now have these sampling offsets, so where to actually look at in the deformable attention. We have attention weights, which again, in deformable case, just are generated from the queries. Then reference points, which are the centers of attention. So to get the actual precise points where to attend to, you take the reference points and add the sampling locations, which basically compute the offset. And then you compute this multi-scale deformable attention function. So all of this should be exactly the same as in deformable data. So then we have 6 of such layers. I've moved one layer up. So after calling the decoder, we get these states out, which are going to be the same shape as the input. And we have states for every layer because all of them are actually going to be used in the loss. So for each of these 6 layers, we get 300 query outputs for each of the 2 images in the batch, and the query dimension is 256. And we return that in addition to the actual encoder output as well, because encoder output is going to be useful to the actual Codetr part of the model. And moving last layer up, so we are basically back to this entire thingy called Codetr head. So we've called the encoder, we call the decoder. Both of them are called the transformer here. So transformer is encoder plus decoder. So let's just continue to here. And then the last part of this actual object detection model is to generate the actual bounding boxes and class predictions. And so here it is done using these CLS branches again and reg branches again. So what happens then? So first of all, we take out this encoder output, which is basically the memory, the giant token sequence of the shape 15K. So we know all the initial image shapes, which allows us to basically find out which token came from which level and which pixel it corresponded to. And we basically iterate and reshape this giant token sequence back into 4 sets of the original images. And then we also have this downsample. So this is like the 5th layer generated out of the 4 layers that we had. So before this, the length of this is 4. So we had 4 levels as encoder input. We reshape them into original shape, and then we add the 5th one, which is just the downsampled version of the 4th. And this downsample is just one convolution with stride 2 by 2, so it's going to shrink this 5th layer roughly in half. Right. So if we continue, now the length of that is 5. Right. Then we need to generate the actual predictions. So predictions are going to be the classification outputs and bounding box outputs. So outputs for classification is pretty straightforward. So we have the CLS branches. So each CLS branch is basically one linear layer. So we have 7 of them in total. So if you recall, we used the last one for encoder projection, and then we have the first 6 for the 6 decoder layers. So the encoder and decoder layers are going to use different branches for classification and regression, but other than that, the logic is the same. A final small detail is that decoder always predicts relative stuff. So the actual regression prediction from the decoder output is a relative bounding box relative to the actual reference points that were passed into that layer. And so to get the actual absolute bounding box out of that, we need to remember all these reference points. And also, as you can see here, to remember which ones were achieved with applying the sigmoid, which ones were not. So all this is carefully handled here. But the point of this all is to just get correct absolute bounding box predictions. And then we return all of this. So we return the actual classification and bounding box predictions, and we'll also return the encoder outputs, because encoder outputs are going to be useful for the auxiliary heads later on. Now, finally, after we've got out the prediction, we are also going to compute the loss, which is part of this codeformable data head call. And to do that, we basically do the Hungarian matching, which is called the one-to-one matching, which is the primary difference of this transforming head as compared to the auxiliary heads. So it all happened in this forward train method. This is the forward train in the same file. So it called the actual model, self from X. This is the forward call. And then we're actually going to compute the loss. So I'm diving down to the loss. The loss is basically this multiply, which takes in, so the loss takes both images from the batch, then the loss single is does it for one image, which is again split in 2 basic parts. So one is the actual get targets, which is the matching process. So which ground truth object corresponds to which decoder output. And then the actual loss computation, which is usually pretty straightforward. So if we dig into this get targets, again, forward's call to get target single, get target single, here it is. So I'm just continuing until here. So it's going to do 2 things that will read this assigner.assign and sampler.sample. And the same logic basically will apply to the convolutional heads as well, but the actual logic inside of the things would be different. So first, the assigner is the Hungarian assigner. So if we look for it, here it is in a slightly different file, so the Hungarian assigner, and we're interested in this .assign method. So let's just continue to here. And we've skipped quite a lot of code, but now let's just see what sort of input do we get? So we have the bounding box prediction, we have the CLS prediction. So 300 queries, each with 400 outputs, 300 queries, and each with 80 class probabilities. And then we have the ground truth, which was passed in to the forward train call, right? So if you recall, we had 6 layers, and the model actually outputs all the intermediate layer predictions as well. So the actual matching is done using only the last layer, and the loss is computed using all the layers. And this is basically the setup. The most interesting stuff is this linear assignment. So let's continue to here and just read around it. So the cost is basically the somewhat maybe slightly different analog of the loss. So we have CLS cost, regression cost, IU cost. So for example, so CLS spread, as we've seen, that's 300 by 80 object, right? And then the ground truth labels is just 3, right? So out of 300 predictions, we need to somehow connect that to 3 ground truth labels. And CLS cost basically computes the matrix of all possible combinations. So the cell in this matrix says how much CLS loss will happen if we connect this particular query output out of 300 to this particular grounded object out of 3, right? And basically the same will happen for regression cost and IU cost. So all of these tell the loss for each possible combination of matches, right? And the final cost will have the same shape, right? And then we call the linear sum assignment, which is again imported from scipy.optimize. So you can just Google it, or we can look at the docs for scipy.org. So this is linear sum assignment. This is the thing that we call the Hungarian matching algorithm or the bipartite matching algorithm. So what it does is it basically takes at this cost matrix, which contains the loss for every possible combination, and it selects the best match. So it will basically select the 3 connections corresponding to the lowest value of loss. And so the matched row indices and matched column indices all have the length of 3. So coming back to the vanilla Decoder slide, this is basically the process of taking 300 query outputs, connecting them to the ground truth objects, in which in our case only 3 of them got connected, so everything else sort of implicitly gets matched to no object. So this is how the matching done. And then after the matching has happened, so we will have this sampling as well. So let's read that too. So here I'm actually pretty sure that no sampling is going to happen, right? So it's pseudo sampling. So the sign result had 3 connections, and then sampling result also has 3 connections. So this is basically not doing anything here, but as we'll see for auxiliary heads, for example, where you have a lot of connections, you might want to sample them to make sure that you don't overthrow your model with negative signal, for example. And then we have the actual loss. So the actual loss should happen somewhere here. Let's read one for CLS, for example. So the shaping logic is a bit weird here. So we actually have this loss single that contains stuff for both images, but for one layer. And then we'll repeat the same thing 6 times for different layers. So CLS scores is an object with shape 600 by 80, so 300 per image, 2 images. And then labels, the shape of that is 600, which we basically got from this matching. So we again skipped some code, but you can see the logic here. So we had 600 predictions and something like 3 objects in the first image, and I don't know how many on the second image. And so everything that was not explicitly connected got assigned this no-object class, index of which is 80. And then some of them got the actual classes. So I think 0 is the person, 25, 16, right? So every query output that got some interesting connection, like 0 or 25, is going to learn to predict that, to detect that. And then everything else just says no object, which means that this particular query shouldn't have predicted anything for this particular image. A clarification about mistake I made earlier. So this loss single function is called for every layer out of 6 decoder layers, which means that the self get targets is also called 6 times, which means that we do get bipartite matching loss for every layer independently. So then we go 1 layer up, basically. So this is the highest level of Codetr, and we're just done with the transformer query head, right? So we've read the encoder, decoder, loss, and then we're just starting the auxiliary heads. So we're basically going to see roughly the same amount of code for this RPN train, ROI head, forward train, this bounding box head, which is the ATSS, and then also this auxiliary forward train for the extra queries. So there's going to be a lot of code. Frankly, this video is getting too long, so I've decided to split that into several parts. Hope that works fine. So just the final outro. So we basically read this part of the model, just the transformer part, which in case of Codetr is nothing new, is just exactly the same as in Dino or in Deformable data, but the actual code is much different to what we had before. So the actual code is the complete rewrite from the guys from MMCV, so it's a bit cleaner, a bit different. And then in the next video, we're going to actually look at this auxiliary heads, auxiliary query setup, and so on. So we have a lot to cover. Hope to see you soon.